Welcome to your exclusive ICSE MasterClass. We're going to demystify chemical bonding today and hand you the exact playbook you need to score full marks on your board exams. I am absolutely thrilled to have you here. Look, today we're ditching the complex jargon and looking straight at the microscopic world in a way that, well, just makes sense. By the end of this explainer, you'll know exactly how and why atoms interact, and way more importantly, how to translate that into top marks. Okay, let's dive right in. Here's our roadmap for today's explainer. First up, the quest for stability, followed by ionic bonds, covalent bonds, and coordinate bonds. Then we'll hit some high-yield exam reasoning. And finally, your ICSE MasterClass next steps. Section 1, the quest for stability. So, almost every single atom in the universe is trying to solve a tiny microscopic problem. They're unstable, they're incomplete, and honestly, kind of naturally stressed out. To fix this, they redistribute their electrons to achieve a stable noble gas configuration. They're basically looking for either 2 electrons in their outermost shell, that's a duplet, like helium, or they want 8, an octet, like neon or argon. To get this perfect stability, atoms are going to steal, give away, or share electrons. Section 2, ionic bonds, complete electron transfer. Let's look at the very first strategy atoms use to get that stable octet. Ionic bonding is essentially a complete microscopic transfer, or you could even call it a microscopic theft between metals and nonmetals. A metallic atom, which we call electropositive, completely gives away its extra valence electrons, and the nonmetal? It's electronegative, so it happily takes them. This creates a positive cation and a negative anion. And boom, they instantly lock together with a massive electrostatic force. Let's look at the first of our mandated molecules for your syllabus, sodium chloride. Sodium has 1 extra electron it desperately wants to lose to become stable, right? And chlorine needs exactly 1 electron to complete its octet. So sodium completely transfers its 1 outer electron to chlorine. This creates a positive sodium ion and a negative chloride ion, giving us the highly stable ionic compound NaCl. Next up is MgCl2. Here, magnesium is sitting there with 2 extra valence electrons, and it needs to get rid of both. So a single magnesium atom transfers 2 electrons, dropping 1 to each of 2 waiting chlorine atoms. The magnesium becomes a 2+ cation, and you get 2 separate chloride anions. Pretty neat, right? And for CaO, calcium completely transfers 2 valence electrons directly over to a single oxygen atom. Oxygen needs exactly 2 to finish its shell, so they exchange those 2 electrons, forming the incredibly strong and stable structure of calcium oxide. Okay, pause right here and listen closely. I'm going to drop a massive insider secret. Examiners consistently deduct marks if you forget the square brackets and charges on your final ionic dot structures. When you draw these in your board exam, you absolutely must draw the bracket around the anion and clearly state the positive and negative charges. Please do not fall into this trap. Section 3. Covalent bonds. Equal electron sharing. So, what happens when sharing is actually a better survival strategy than complete transfer? Well, neither nonmetal wants to completely give up an electron, so they compromise. Depending on what they need, they might share 1, 2, or 3 pairs of electrons. If they share 1 pair, that's 2 electrons total, making a single bond. 2 pairs make a double bond, and 3 pairs make a triple covalent bond, exactly like we see in nitrogen. Take methane, for example, another one of our must-know molecules. The central carbon atom needs 4 electrons, and 4 individual hydrogen atoms each need 1, so they form 4 single covalent bonds. Because they pull on these shared electrons equally, there are no charges created. It's a perfectly balanced, nonpolar compound. But what happens when sharing isn't perfectly equal? Thanks to differences in electronegativity, we get polar covalent compounds. Look at water and ammonia. Oxygen and nitrogen pull slightly harder on those shared electrons than the hydrogen atoms do. This creates slight positive and negative poles, making them polar molecules. This distinction is a huge favorite in your exams, so definitely keep it in mind. Section 4. Coordinate bonds. The lone pair. Now, this is where things get really fascinating. A coordinate bond is technically a covalent bond, but with a twist. 1 atom provides both electrons for the shared pair. We call these unused pairs of electrons a lone pair. The donor atom basically gives this lone pair as a piggyback ride to an electron-deficient acceptor, usually a hydrogen ion that has absolutely no electrons of its own. You absolutely must master these 2 specific structures for your board exams. The hydronium ion, formed when water donates a lone pair to a hydrogen proton, and the ammonium ion, formed when ammonia does the exact same thing. In both cases, notice how the central atom already had its stable octet, but just had a spare pair of electrons sitting around doing nothing. And here is your next ICSE MasterClass survival tip straight from the examiner reports. When you draw a coordinate bond, you cannot just use a simple straight line. No way. You always have to use a directional arrow pointing from the donor atom directly to the acceptor atom. If you draw a regular line instead of the arrow, you will absolutely lose points.
Section 5. High-Yield Exam Reasoning.
Let's see how this microscopic bonding translates into the macroscopic properties you see every day. This is a guaranteed area for board reasoning questions. First up, melting points. Because ionic bonds are formed by oppositely charged ions, they have incredibly strong electrostatic forces holding them together. Think of them like super strong magnets. They require massive heat energy to break apart, which means very high melting points. Covalent molecules, on the other hand, just have weak intermolecular forces, so they vaporize and melt really easily. Next is electrical conductivity. Remember, solid ionic compounds have their ions completely locked in place, so they won't conduct electricity as solids. But the moment you melt them down or dissolve them in water, those bonds break. Those free, mobile ions can now carry an electrical current beautifully. Covalent compounds, since they're just sharing electrons and have no free ions, they are completely non-conductors. Section 6, ICSE MasterClass Next Steps. All right, you now have the exact blueprint for chemical bonding, but your board exam preparation doesn't stop here. To make sure this information really locks into your memory, navigate to our channel bio right now. We've linked your free handwritten lecture notes and formula sheets in the community links. Go download them immediately. And hey, be sure to hit that subscribe button to ICSE Masterclass to unlock our full syllabus map series designed purely for your academic performance.
So, the real question is, are you ready to absolutely crush your chemistry boards beyond the exam? Then next time you look at a simple grain of salt or a drop of water, ask yourself, what invisible, microscopic forces are silently holding your entire physical world together right now? Use what you learned today, dodge those examiner traps, and I'll see you in the next ICSE Masterclass.